So hey guys, welcome to week 6 of Techquitable. Today's lesson will be focused on the topic of recursion. And before we start, just one announcement is next week we'll have a break due to Thanksgiving. So please have fun and enjoy your time with friends and family. But with that, we'll get started with today's lesson.
Awesome. All right, let's start presenting. Okay, wait, you guys can see that, right? The entire screen?
Yep,
Okay.
it's covered.
Cool. So, what the heck? Can't, okay. So Wenta, is this you?
Oh yeah, yep. So just to kind of go over the agenda for today, we'll first do introduction and a little bit of background of our presenters today, which are Curran and Alan. And then we'll get started with the actual material, which would be the recursion. So first going over the definition and basic examples. And then after that, we have 3 example problems that are ready to be presented to you guys. One is on a problem called symmetric tree. The second problem is on sanitizing an object. And lastly, we'll be counting paths and how we can do that with recursion. So yeah, so lots of problems to get through. And then lastly, as usual, we'll leave Q&A, the last 5 to 10 minutes portion.
I guess we'll introduce ourselves. My name is Karan. I'm currently a software engineer at Salesforce. I went to the University of Illinois at Urbana-Champaign. And yeah, Alan.
Yeah, hi, nice to meet everybody. I'm Alan, currently a software engineer at a super small startup called Lido in New York City, and I went to Princeton for undergrad.
Cool.
Awesome. All right, so let's just go over recursive definitions and examples and just talk a little bit about that. So, I mean, everyone, I think, probably understands this by now, but basically a recursive function is a function that calls itself. More on that, the typical format will be a base case and then a recursive case. Generally, the recursive case could be counting down to the base case in a simple example. By the way, feel free to ask me any questions during the presentation. You can either say it or message it to me. All right, so thinking about recursion. So one cool example is the factorial function. And we can kind of see like, okay, the factorial of 4 would be 1 times 2 times 3 times 4. If you go and look at factorial n, it equals factorial n minus 1 times n. And it's recursive, but something's wrong. Can anyone see why? All right, let's see why. It recurses infinitely with no base case because it just keeps doing n minus 1. It can go on forever. So what would be the base case in this scenario? Alan, do you know?
Yeah, so right, factorials don't go negative, so it had to stop at perhaps 1.
Yeah, exactly. So yeah, if n is 0 or 1, we want to return 1. And then else factorial n minus 1 times n. So yeah, it's important to think about the base cases and make sure you actually hit them. Otherwise, your recursive function will go out of whack and it'll just keep going and your code will not work. So, all right. I feel like, does anyone, yeah. So everyone here, message what you think the factorial function should look like. Let me see the messages. That includes you, Alan, and Wentel.
Sounds good. Yep, and then just to kind of like highlight the problem for everyone, we're doing this problem of factorial, right? And then we're just assuming this input of n for now. Is that right?
Yeah, so in any language, give me your function for factorial. Ooh, hey, Ayo's here. Nice. All right, I guess I should do it too. Nice, Valerie. All right, so if we have, that's probably Java or, Oh, nice, nice. Okay, we got it. Oh, is that a lambda? Or I guess I don't know if it's, or not a lambda, but a what are those functions? Yeah, I think it is a lambda.
Oh, it's just an arrow function in JavaScript.
Hmm.
Yeah, I know it looks like one in other languages.
Yep. And then
Oh yeah, that's true. Oh yeah, of course. Because const is not in Java. Okay. Anyway. Nice. Wow, I'm actually pretty impressed. Everyone actually wrote the code. Nice. Good participation. Oh yeah. All right. I'm assuming everyone sent it by now. And then I'm gonna go back to presenting. Great job, everyone. So yeah, I kind of dumbed it down, but yeah, this is the very simple Python. If n equals 0, return 1. If n equals 1, return 1. And then factorial n minus 1 times n. All right, can we get some guesses for, oh shoot, for big O time and big O space? I'm gonna call on you, Io.
Oh, wait, sorry. Can I process it first?
Sure, actually, let's do, oh, okay, I see. Dario says O of n and space O of n. Yep, that's right. It's O of n and O of n. Keep in mind that the O of n is on stack, so it's like it's happening in the background because there's no actual data structure that's being used. We never assign anything.
well, wait a minute. Instead of the time complexity being O of n, like for each factorial, right? So for each value, doing 2 multiplications, right?
Sorry, say that again.
Oh, so yeah, I was kind of like wondering if it's like more complicated than just time complexity or runtime of O of n. Just because for each value leading up from like 1 to n, we're doing multiplications of like, you know, just like n number and any kind of factorial number, right? That will be passing on the recursive call.
Yeah.
But there's some repeated calculation that's happening since, you know, anytime you pass in like any kind of n minus 1 to factorial, it's going to do all that kind of a similar calculation down, you know, again and again until like n gets down to like 1 or 0.
Yeah.
That's the same, like, you know, even if you pass like some kind of value into like the factorial function, and then, you know, any kind of like value that's like 1 less than that, and you're doing that many times. So that kind of feels like it'd be more than O of n. If that,
well, hold on. All right, now I like this. Let's talk about this a little bit. So let me just draw it out a little bit. Let me duplicate this slide here. Since we're talking about it, let's do that. So I'm just gonna delete this right here. So factorial, let's say 6, right? Would go in and then would return n, so 6 times factorial 5, right? Which then would return 5 times factorial 4. And then it would go on and on and on until it hits 2 times factorial 1, right? Which would be 1. Which would just come off as 2. So what is repeating?
Yep. So yeah, we actually see that only the factorial functions are just getting repeated call, right?
Yeah, but it's only gonna happen n times. Like factorial will only be called n times. And I guess what's being stored is the number. Huh. Alan, you want to chime in here?
I also think it's n in this case. Because like there's no branching anywhere, right? It just straightforward goes down.
Yep. Yep. Got it.
So it takes the number 6, right? And then it'll go into 5. And then it'll do 5 times. Well, I guess it would do 6 times 5. Right? Or 6 times factorial 5. And then you would go solve for factorial 5. And then, okay, so this is where, so this is 2. Or sorry, this is 2. This would be something else. So it goes back up, right? So
Yep. Yep. No, this is super clear explanation. Yeah. So it is O then.
okay. Space complexity wise. All right, well, if we have more time, we can go over it more, but let's go back. Okay, so let's talk about Fibonacci. The formula for Fibonacci is fib n minus 1 plus fib n minus 2, where fib 0 is 0 and fib 1 is 1. And this is kind of the sequence as it goes: 0, 1, 1, 2, 3, 5, 8, 13, 21. So basically, the last 2 numbers added together make the next number. Okay, let's see some code for this. This will be interesting. For the Fibonacci sequence. All right, I'll start writing as well. Oh, well, need to not do that. Go back.
All right. Wow, we got a couple of submissions already.
Nice, nice. One, then else. And fib, and minus one. Times fib minus p. Cool. Okay. Nice. Nice. I love the participation, everyone. This is great. All right. So let's get back to it. So yeah, this is the Python solution. If n is 0, 1, return n. Otherwise, return fib n minus 1 plus fib n minus 2. Oh, okay. So big O time. Let me see if people are messaging. Going back to what I said previously. All right, so looks like Ayo and Valerie are spot on. So basically each state meaning a call to Fibonacci generates 2 other states. So yeah, the time complexity is 2 to the n. Awesome. Yeah, glad we got that one out there. So I want to stress something. When you're writing recursive functions, I think it's important to draw out your functions. Actually, in general, drawing a diagram really helps basically like code better. When I code, I always have a pen and paper next to me, drawing out diagrams, figuring out what's going to happen, and drawing out scenarios like, okay, if I have Fibonacci 5, what would be 4, what would be 3? And I hope everyone here when they code has a pen and paper as well. So yeah, now let's get to the first example.
Oh, let's see. Oh, Karan, I have a question. So
Yeah.
for those who are like not too familiar with time complexity yet, can you explain to why the base is 2 and is raised to the n power?
Sure, yeah. So I guess like a simple way of explaining this would be that if you look at F5, when you go to the next when you go into the F5 function, you're going to call Fibonacci twice. So you're going to call F4 and you're going to call F3. And then when you go into F4, you're going to call it twice as well. And then F3 is also going to call it twice. So that in there, you can kind of see how 2 keeps on multiplying. Now, I was actually discussing this with Io last week too, but basically look at the number of levels. So F5 is the top level, that's 1, and then F4 and F3 are 2, and then 3, and then there's the 3rd level, there's a 4th level, there's a 5th level, right? And if this was all filled out, if the bottom level was all filled out, then I think that would equal 2 to the 5th power. And yeah, so 2 to the 5th power is what? 4 times 4 times 2. So 16, that's 32, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And then this would be 16. So it would be 31, right? If you filled out the entire bottom level. Now, so that's just kind of like a general like explanation of like the function splits into 2 every time, and that's why it's 2 to the n.
Got it. That's super clear explanation.
Cool. Thanks, Wental. All right, let's go to the example. All right, so the first example is a symmetric tree. So here's the problem. Basically, you get a binary tree and you have to check if it's symmetric or not. So does everyone see this example? 1, 2, 2, 3, 4, 4, 3. So does everyone understand that on the left side, it's a mirror, but on the middle case, it's not a mirror because there's a 5 in the place of a 3. And on the rightmost side, it's not a direct mirror because 4 and 3 are interchanged. So that's just an example of the problem, 3 examples of the problem. And yeah, they kind of talk about it more. If you were looking at this recursively, you would go down 1, you would look at the subtree. You would basically take the big subtree, you would take the tree and make it into subtrees and then make it in even smaller subtrees such that 3, 4, 4, and 3 would be trees itself, but those would be base cases. They'd be called leaves. So yeah, just think about it. What conditions should be true for a tree to be symmetric and what should be our base case? I think I already kind of alluded to what the base case should be. So the conditions that should be true for the tree to be mirror images. The root nodes have to be the same. The left subtree of the left tree and the right subtree of the right tree have to be mirror images. And then the right subtree of the left tree and the left subtree of the right tree have to be mirror images. I hope everyone's following this. I think visually it makes a lot more sense. And yeah, the base case should be the end of the tree, the leaves. Oh, wait. All right. So this is kind of a basically one version that's not completely filled out of the solution. And can we get everyone to try and write this out? So I'm going to go back to the diagram, or actually, So this is the diagram, right? And then this is the recursive solution. I wonder if I could put them next to each other. Let me see if I can do this. Here. Yeah. So this is the diagram, and this is the solution. Well, this is part of the solution. Can everyone else write out the rest of the solution? I guess it's just the check symmetry and the root too.
So just to highlight the kind of like the function setup here, that is symmetric function is the main function that takes the root of the tree. And then it calls this helper recursive function called isMirror. And this isMirror is supposed to like be implemented in such a way that it's supposed to check whether the left subtree and the right subtree are kind of like mirroring each other, right? That's why you're passing in like the two kind of like a two like nodes or two roots into this isMirror function, right? Is that right?
Yeah. So like I think a big thing also is you would have to figure out what data structure this would be, right? Like what's the node? Is it a struct to you? I guess, yeah, it could just be any old Java object. So you kind of have to decide that first, then you have to make a base case, then you have to figure out how to check symmetry in recurse. It's a little complicated, so yeah, it could take a while. All right. How much longer should I wait?
Let's see, is anyone close to getting it? Well, this might be a hard problem, so we might have to just go through it together as a class.
Okay, that's fine. All right. So yeah.
And Karen, I can bring the diagram over so that it's easier to explain.
Oh, thanks, Wintel. So yeah, so in this scenario, they basically just said, if the root is none and root 2 is none, return true. Basically, if they're not there, return true. And then, actually, let me start from the beginning, like Wintel was saying. So when you call this function, you're going to call it from is symmetric. Then you're going to call is mirror, and then you're going to put the tree into both sides. Root. So is mirror is root and root. And then is mirror treats them like separate trees. So if root 1 is none, and if root 2 is none, it's not there, return true. If both are there, yeah, if both are there, then check if they're equal. And then recurse. Otherwise, return false. So let's look at the recurse function, not function, the recurse code. And it would be return mirror, return is mirror root 1 dot left and root 2 dot right. And then root 1 dot right and root 2 dot left. So yeah, so basically if 2 is root 1 and 2 and the sorry, if the left 2 is root 1 and the right 2 is root 2, then root 1 dot left would be 3 and root 2 dot right would be 3 and root 1 dot right would be 4 and root 2 dot left would be 4. I hope everyone can kind of see that. Thank you, Ariana, for telling us that. Does anyone have any questions about this or something that I should go into more? I realize this is I'm like circling my mouse. I don't know if people can see that though. So let me see.
Yeah, we can see it.
Oh, you can see it. Okay. So then I hope that helped a little bit more.
Could you explain the return again? I know you just said it, but just one more time. Sorry about that.
Sure, sure. The return, you mean the return true?
No,
Oh, you
the
mean
other
the
one.
return is mirror. Ah, okay.
Yeah.
Sure. So let me see if I can insert a text box here. So kind of what's happening is when is mirror is getting called, so is symmetric gets one, right? It gets the whole tree. And what it'll call is mirror 1, 1, right? I'm just gonna go through the whole thing like this, and then you guys can tell me if you want me to explain the. I mean, I realize you want me to explain the return again, but I'll get there. So is mirror 1 and 1. So in this case, root 1 is equal to 1, and root 2 is equal to 1. Now keep in mind that root 1 dot left is equal to 2, and root 2 dot right, root 1 dot right is also equal to 2, and then root 2 dot left is 2, root 2 dot right is 2. Does everyone kind of see that? Does that make a little sense?
Yeah, it does.
Okay, and then what we're gonna do is we're gonna go through that second if statement. If root 1 is not none and root 2 is not none. Basically, if root 1 and root 2 are both there, which in this case they have to be because they're both 1, then it's gonna go in and ask, is root 1 and root 2 equal to each other, which they are because it's the same item. And then it's gonna return is mirror root 1 dot left, which equals 2. So it's going to return 2, 2, and is mirror 2, 2. And then let's go in the next example just to really hammer this in. So is mirror 2, 2, root 1 equals 2, root 2 equals 2, root 2 dot left equals 3. Sorry, root 1 dot left equals 3, root 1 dot right equals 4, root 2 dot left equals 4, root 2 dot right equals 3. Then what would happen is return is mirror the left and the right, the root 1 left, which would be 3, and the root 2 right, which would be also 3. And is mirror 4 and 4. So I can draw or highlight. Can I draw?
Yeah, and I just looked this up. Go to
Insert.
line,
Okay,
scribble.
nice. Okay. Oh yeah.
Has to be
So
one continuous stroke.
okay,
I think
okay.
yeah.
Thanks, Alan. So this is mirror. Is this? Oh, no. Crap. Is dang. Is this 4 and 4? And then this is mirror. Oh, I have to press insert scribble again. Okay. So this 4 and 4 is this 4 and 4. This 3 and 3 is this 3 and this 3 and that 3. Cool. Okay. Does that kind of make sense?
Yeah.
Okay. Cool. Thanks, Ariana. All right.
And to highlight one more interesting about this function, I mean, the is mirror helper function is just doing a lot of work here. Especially the line that's like kind of calling the kind of like the branching state of is mirror, like root 1 dot left and root 2 dot right, and another like set of like is mirror like recursive call of like root 1 dot right and root 2 dot left. So that's like where the branching is happening because like it's making the two recursive call. And top of that, because we want to check if the tree are symmetric, if the tree is symmetric. So in the end, what we want to return is like a Boolean value of like true or false, right?
Yeah.
And that's fascinating that those like two recursive function calls is kind of like joined together with the AND operator, right? Because then that's like, that means that, you know, any kind of return values that those recursive function call is going to return, they
Mhm.
both have to be true in order for that last return to be also true as well.
Yeah. No, yeah, exactly. So anytime anything becomes false, it automatically just is done. Right? Like if any of them immediately become false, if like, oh, this mirror is not correct, then it'll be false, and then it'll immediately basically just invalidate. Like it'll still go on the other side. Like it'll still keep going, I assume, but once one of them is false, the entire function will be false.
Yep. Yep. And then this is like also like pretty stereotypical of like recursive function call, but you know, you have this helper function that's doing a lot of like heavy lifting work. And the first part is like where you're kind of checking for the base case, which is happening with our check here, which like if root 1 is none and root 2 is none. Because that means that we have like reached like this like leaf nodes or basically like the bottom nodes in which like there are like no more like Trojan nodes, right? So we're kind of trying to detect for that base case, and if they both happen to be like none or do not like don't exist, then that's when we just return true and start passing that value back up the chain. But otherwise, we're checking for like other cases where if root 1 is not none and root 2 is not none, that means that we're somewhere in the middle of the tree, or it could be the top of the tree, and it has just a bunch of like children nodes going toward the bottom. And then that's where we kind of like setting this up to basically make more recursive function calls.
So that's a really good point, Wentao, that the leaf nodes are also the base case. If everyone realized that, like this 3 and this 4 are root 1 is, oh, actually, sorry. Ooh, wait. Actually, when you're on 3, then the root left would be, so it's okay, sorry. I want to recorrect my statement. When you get to 3, the 3's left and 3's right would then be the base case. So the leaf nodes, I guess, aren't the base case. It's the leaf nodes children that are the base case. But yeah, awesome. All right, I'm gonna hand it over to Alan now. And I think I'll stop presenting. Is that cool with you, Alan?
Yeah, works for me.
Awesome.
Oh, wait, I had a quick question.
Oh yeah, I'm gonna touch up on this too. So yeah.
Okay.
Let me see. Does this work for everybody?
Yep, we can see it.
Okay, cool. Yeah, what was your question?
Yeah, I just wanted to confirm the time complexity for this.
Mhm.
I'm assuming it'd be O of n.
Why do you think that?
Well, we're like iterating through like all of the nodes in the tree, right? And so, yeah, I guess that's where my thought process came from. We're iterating through like all the nodes of the tree, so that's why it's O of n.
Yeah, no, you're right. Sometimes, yeah, just because it's recursive doesn't mean it has to be some fancy exponential or log function, right? So you're spot on. You have to check every node to see if it's balanced. So what I was gonna say is, I think that with recursion, we all say that, hey, the body of the function, you're gonna find the base case to stop infinite looping. And then you're gonna have the rest of the logic that calls itself. I personally also find that it's easier said than done to recognize the base case sometimes. And I think for trees, something that may help if you're ever stuck on a problem is, I find that oftentimes the base case is the last layer of children that aren't drawn. So sometimes maybe just like writing it out and realizing, hey, it actually stops here at the leaf node, the nulls. It just helps me kind of solve these problems, or sometimes it's hard to think of where it stops. Right, and like Corinne was presenting, like it actually stops here because once you're at 3, you actually look at its children, and then they don't have any children, and that confirms that that's like the leaf, and you can like you've safely iterated through both 3s on the edges of the tree, and that they match. Another set of tree problems that I've seen are like, given an array, you construct a valid BST. Sorry, given a sorted array, you construct a valid BST. And it's also hard sometimes to think of like, where do you actually stop? And oftentimes the stopping is like, you get to the 3 and then you actually attach the nuns to it, because that is what the actual structure, right? Like there's invisible none left and right children for all of the leaves. Okay, so the next question
we
is,
had one more follow-up question from Dario
sorry.
asking, like, what is n here? Sorry. I guess it was asked in the context of answering time complexity.
Yeah.
But just to answer myself, so n here is the size of the tree here. And inside the tree here is being defined as like number of like nodes in the tree. So yeah, I know it's a little confusing because we always kind of like implicitly kind of define or assume that n is just like size of something, right? But in this case, we're just assuming for the size of the tree here. Yep, just to kind of like answer his question.
Yeah. Oh, sorry, I couldn't see the chat. Can you guys see the chat on my screen now?
No, but it's fine. We can also help monitor and let you know if anyone raises.
Okay. Yeah, thank you. Okay, so for the next question, it's going to be sanitizing a JSON object. So just before we start digging into it, does everyone here know what a JSON object looks like?
Kind of.
Maybe talk about it a little bit.
Yeah, just wanted to get a pulse. Yeah, so here's like one example of it. It's just a very commonly used format for like code to talk to each other. Like if I want to, let's say I want to see what my favorite most listened to songs on Spotify are. Spotify maybe has an endpoint that will give me that information, and then if I write code to ask Spotify, they'll often respond in something that looks like this. So I think actually the next slide is a better picture. So here is like what a typical JSON object can look like. As you can see, in the simple case, it's like a string or a number. Typically, there might be a Boolean, but there's also situations where it's not just one level deep. So for dogs, right, it's an array of objects. So, and for veterinarian, you can see it itself is an object. So I would say there's like, I would probably divide a JSON object, the values into 2 sections. One where it's just a simple primitive, like Marcus Schroe, and one where it's like dogs or veterinarians or cats. So also like in the previous slide here, see, we can have dictionary values like pet names or employer, which are a little more complex than the other fields. So in this problem, we're going to try to sanitize password out of a sample JSON object. Does everything make sense so far?
Yes.
Okay, thanks. So here in the example, you can see that corgi is classified information, and we don't want just anybody being able to view that. So the task is given this user object. How do we obfuscate that value from other people? So does anyone have any high level ideas of what they might do?
Can you repeat the problem again?
Yeah.
Oh, yeah. Okay, so sorry if I didn't explain that well. So you see how on the left and the right, the difference is that corgi is now 3 star, has been replaced by 3 stars.
Oh, so anywhere where the password is located, you have to.
Yeah,
Interesting. Okay, but corgi is like when you say it as a breed. So basically you take the password and then anytime that password appears anywhere else, you have to exit out.
yeah.
Yep. And I guess one little bit of confusing thing here is that the password, if we kind of specify the keyword here to be corgi, it can also like appear in like more than just like this field called password. Like for example, here in this example, it's also showing up under this like field name of breed under the dogs. And there we want to also sanitize it so that it doesn't show up as well. And that's a tricky part because it's like, if you just look for the field name with like password, you like also miss like other fields that could potentially contain that password. So
I think Dario has his hand raised.
Yeah. Hey, Dario.
Yeah, I have an idea as how to approach this problem.
Okay, yeah, please.
I think I would use if we want to do recursion, we do a recursion on the object, which is going to be the JSON. And whenever we encounter, and for every one of those keys, we're going to see whether or not it has more things into it. Because I noticed that every key that has more information into it is contained within some sort of object, array. So if we look at dog has an array that has, more objects in it. So we recurse for every one of those keys, and if there's more information, go deeper into that. And whenever the given word it's found, then we can just take that and change it for 3 stars or whatever you want to do. So my function will require the JSON and also a word to replace. So like in this case, it will be corgi, but it could be anything.
Oh yeah, I think we probably, with your explanation, we've gone a little bit ahead, but yeah. So I think that's a very solid top level approach, right? So like you were saying, you basically outlined what we have here in the slide. Yeah. So this is kind of like some pseudocode, kind of illustrating your idea. Can you tell me what additional thing we need to do here?
As in like, what exactly do you mean?
Oh, like so this is like just follows your general idea of how to kind of like navigate this JSON object, which can be structurally n levels deep. So what additional kind of like, where does these 3 lines of pseudocode fall short?
Right, so the loop is only checking if you have a string, but we need to check if we have more stuff in that string, like an array or something. So that would be part of the else part. I'm looking at the dark thing there, yeah. So there you need some sort of else to, deal with that thing, and that would probably be recursion.
Okay, yeah, let's go on to the next. Yeah, exactly right, right. We can't just, it's not just a string or an object. There's another case. So here is kind of like the high level pseudocode. And it's exactly what you outlined, Dario. Does anybody have any questions up to this point? Okay, yeah, and I can just like run through the example really quick. So right, we have three cases if the object is a string, if it's an array, or if it's an object. So let's just start with string since it's the simplest case. So back to the example, if password is string, so we check name, we check password. Okay, we find a match in address, so we just replace it. So on the first level, this is already done. But when it gets to dogs, we go back to this function, it goes into this array. So now we say, okay, we have to iterate through the array. And now as far as the function is aware, all you see is this now in the second call, right? So when we are effectively here in this function, oh, sorry, that is a terrible scribble. So once we're here, we're gonna now pass in, we're only gonna pass in this object. And then on the next iteration, we're gonna pass in the one below it. But as you can see here now, this just becomes a string once again.
So Alan, question. So basically you just get a set, like for the top if statement, you're basically taking the whole sentence and then wherever your password is, you just replace that one part. That's what that line does, object replace.
Yeah, yeah. Oh, sorry, I should have explained that more. That it's also, this is all just kind of pseudocode. So yeah, we can just say object replace. Given the password in a string, it just replaces it. And we don't have to like write the code to do that.
Okay, so is that the base case? The object is a string?
Yeah, oh well, what does everybody think?
Ariana says yes.
Yeah,
Mostly.
yeah. So
With the lulls at the end, but
that is exactly correct, right? So going back to like Fibonacci or the factorial, this is when n is 0 or 1. When it's a string, we can just check if it's in the string, because if it's not, we need to dig deeper. So then the two below it, the array case and the object case, would be the equivalent of like fib n minus 1 plus fib n minus 2. So the cool thing about this is, I've actually written something similar like this at work too. So like, it's very common, like I was saying, when computers are talking to each other, that you get data in JSON, and sometimes you want, maybe your company wants, gets an idea of what the JSON looks like, right? And you don't know because JSON is, the structure is arbitrary, right? And that's why we need something recursive, because we don't know how deep it could go. So oftentimes maybe you want to obfuscate something like in this example, and you can also, or you can go through, let's see this, right? Like, let's say I want to get a data model for this user, and I don't know what the user looks like. One way to do it is like, instead of just obfuscating the password at each step, we can say, hey, what type is name? And then you can run your language's native type function to tell, and you kind of can build your own model of what a user looks like. And it would be more or less the same logic here, just the end step, you do something different. Instead of replacing the password, you just check what the type is and you save it. Okay, does anyone have any more questions on this example?
Wait,
Okay.
hold on. Where's the base case in this function?
This is a slightly different.
Oh, I guess it's,
I think that the base case is the lack of having a complex object, in which case you just return.
oh, okay, so this is not exactly the same as the pseudocode.
Yeah, sorry, this is slightly different, but this is something that would be written at a company potentially. Okay, well, let's move on to the next, the final example. So given a grid with some cells blocked off, find the number of paths from the top left to the bottom right. So let's just show this because it's easier to see it. So we just want to find the number of ways someone can go from the blue dot to the green dot. Let's see. Okay, I'm going to draw a little bit. So see this one, I'll start here. It's fairly simple. You kind of only have two options. Can everyone see what the three ways of getting from here to here is?
Yeah, I think Dario has his hand raised.
Okay, yeah, Dario.
Here we can do recursion, which would not be my first approach, but we can do recursion and see if we can, go to the final destination within one route and then see if we can get it through the other route. Because I'm thinking about using a queue, and in a queue we add to the top, remove from the top, and so we're only gonna explore one path, and then we go back to the previous thing that we had at the beginning, and then explore that path. And every time we reach the end, we keep a counter. We sum, let's say, the counter +1, and then after we explore the entire queue, then that must mean that we have found all of the path. If there is an X in the path, then we cannot add that path because I'm assuming that we cannot go through the X, and that way we're only gonna find all the paths that are valid. But I don't think that would be my first approach to this problem.
Okay, cool. Yeah, that sounds like a reasonable approach, but why do you say this wouldn't be your first? What else do you have in mind?
Using a queue will be my first approach, just because it's how I logically think,
Mhm.
and it will be easier for me to follow that way.
Okay, cool. Let's see. Okay, I think this illustrates here. So as in you would queue each cell you're exploring, and then once you're done exploring, you would dequeue that and then queue the next one.
That's exactly what I had in mind with the queue.
Yeah, that's and then so your solution would be iterative, is what you're saying, right?
Yes, because I don't know if there is a way that I can do recursion with a queue. There must be, but not that I'm aware of.
I think you're spot on. It's like, as long as there's a way of keeping track where you have explored and where you're going and where you need to go. And recursion is just one tool. And if queues make more sense to you with the iterative approach, that's it's equally as valid. And also, I remember in the chat earlier, people were talking about dynamic programming. This is actually also an excellent dynamic programming problem as well. So there's just multiple ways to solve this problem. But let's dig into
With
some more.
sorry for interrupting. With if you have like a set that keeps track of the rows and column you have visited, would that be the recursion? Would that be the dynamic programming part?
I would, so I also don't know the fully academic definition of dynamic programming, but I would say that's just like an extra data set to kind of help you on your journey. It's usually, so do you know, how would you define dynamic programming, Dario?
I would define it as a way for you to now repeat your steps. So if you can express a problem within like a problem that has sub problems, then you don't have to redo the same thing you did again. So if we go all the way back to when we were talking about the Fibonacci sequence, when you said Fiv of 5, you had to redraw the same tree over and over again. So look at Fiv of 3 is also found on the left tree. So if you can store the answer for Fiv of 3 every time you encounter Fiv of 3 again, then we don't have to go down the whole recursion. We can just, oh, we have it already. We just use that answer instead. And so that would be one of the definitions that I would give for dynamic programming.
Okay, cool. And what were you saying though? You were saying you want to store the set that you've seen?
Yeah,
what exactly do you want to store?
So if you look at this as a grid, so you have rows and columns. If I have visited something already, I want to put it on my set so that I don't have to visit it again. Does that make any sense? So that is going to it's going to prevent me from going down the same path over and over again, or visiting the same location more than once.
No, that is true. But actually, with dynamic programming, I think you could take that a step further as well.
How so?
So how do you envision, so let me draw this out.
So if I'm hearing Dario's proposed solution, right, he's actually thinking about like a best first search, starting from the starting point. And then each cell or each place that he visits in the graph, he's going to pass it off to this like the dynamic part or this memoized part, where he's going to say, hey, I have already visited this location. And I'm going to also just write down how many paths I have, like how many paths it is possible to get here, right? And then as he kind of count that, he eventually will get to the finishing point, and then just like tally up all those counts. And this is like where also the queue comes in, because queue and best first search come in hand to hand. Where a queue will basically like help the kind of like the order of traversal in this best first search approach. So yeah, Dario, I think that is a pretty cool solution, and I could definitely see it work. But just like as a general rule, like you can kind of associate a queue being like a helper data structure to manage your like a best first search type of like a traversal. But anytime like you use recursion, you are technically like working with like this kind of implicit stack that you may not notice like kind of like using because like with recursion you would just call the function itself. But then do you know that there's kind of an implicit stack that's like keeping track of like, yeah, what are the states that you're calling those recursive functions from? Because as you kind of like traverse back upward the stack, you need to kind of visit the caller again to kind of like do any kind of computation or to tally up whatever kind of like values that you got back from your like other basically other callee functions, right?
Yeah, when we do recursion, don't we use the call stack as like the implicit stack? And when you put something on top of the stack, you go there next, just because of how the natural order of things work.
Yep, exactly.
Yeah, so yeah, like with but going back to fib, right? It becomes quote unquote like dynamic when we cache this value. So the left side of the tree doesn't, or sorry, the right side of the tree doesn't have to recompute f of 3. So I think if I'm understanding what you're saying correctly, the queue to me seems like it's just kind of like keeping track, but it doesn't necessarily like save computation. But we can, let's just dig into the example so we can see what is going on. So. So let's think about this problem. Let's just start from here. How many ways are there to get from A to the end right here? Oh, and sorry, I can't see the chat in this mode anymore. So if anyone could help me out.
I'll let you know if someone chats.
Okay.
Dario says 1.
Mhm. And what about B?
Dario says same.
Yep. So now going a step further, how many ways can we go from C to the bottom right square?
Ariana says 2.
Yep. What about D?
Dario says 3. I say 2.
Yeah, I'd agree with 2. Dario, where's the third path?
No, I actually agree with 2.
Yeah, because like you can't go down on the first square. Okay. Yeah, because right, like as we're moving away from the base case, that's why we need the algorithm. It just doesn't become as obvious anymore. So right, like now it's kind of, we kind of have to keep tracing how many paths from X. But let's just see. Does anyone know how many paths from X?
Oh man. There's got to be a formula or something. I don't want to do this.
Yeah. Well, I have a number that I think is maybe correct. Anyone else also want to give a shot?
Can you please repeat where from where?
From X. Sorry.
I have a rough idea. I didn't count correctly.
Mhm. All right, what you got?
6.
6. All right, I think I have 4, but also I could have not counted correctly. But yeah, see, it's tough. This more so illustrates that we need a function for this because humans are, we can spend our time doing other things than trying to see how many paths there are. But kind of going from A, B, C, D out to X, Y, and then the corner, does everyone kind of see how this problem can be broken down?
Yeah, basically you would start from like C, like you would get to C and then you would recurse on C, right? Like, and B,
Oops, yeah. So, right, like the logic was, and similarly from C to A and from C to B. So you can see that like from A, there's one path to the end, from B, there's one path to the end. So since C can reach both paths with one path to the end, right, then C has two paths. And the reason that D doesn't have 3 is because it can't go down, but D can reach C, and C has two paths, so D has two paths. So you can see that path here. That's why they were saying path xy equals path x plus 1y plus path x y plus 1. So if path xy was C, then the one's an example at least, path x plus 1y would be A, and then path x, the other one would be B. So C equals 2. Whereas for D over here on this square, C is 2. So the first value here would be 2. But when you cannot go down since there's an obstacle here. So it's 2 plus 0. That's why D is also 2. So can anyone think of what the base case might be?
I think one of the base case would be if you made it, like if you made it to your final destination.
Mm-hmm. Yeah, exactly. So here, for at the end, return 1. If we're off the grid or on an obstacle, return 0. So that makes sense in the case of all of these, right? A, you hit the end, that's 1. That's why the function, when you call it with A, you get 1. Same with B. And then D illustrates the other case where if you go down, that path hits an obstacle, so that returns 0. And similarly, if you're over here in this corner, if you go down, you go out of bounds. So that's invalid. That's also 0. So kind of putting that into code, right? You see here on this return line, this maps back to this line here. And these are our two base cases. And yeah, I think also oftentimes with these recursive functions, there's a lot packed into a few lines of code. So you can be surprised sometimes where you see a problem and it is a really difficult problem to kind of think about. I think it's really helpful to, like Corinne mentioned, you have a pen and paper next to you and you kind of draw out the cases and you kind of write out the base case, like what would be a base case and where you would need to keep going. Like in the tree example, also in the JSON example, right? If it's an object, and here, if you're not at the bottom right corner, if you're not at an obstacle, and that will really help you to put all your thoughts into code. And I think that this step is also not very easy to do, but it gets better with practice.
So Dario just commented, what if I put you on the middle of the grid and ask you to count the number of times you find C? Let's assume you are a bunny trying to find all the carrots. Would the same approach work?
Put you in the middle of how many times you find C?
I asked you to count the number of times you find C. Dario, you want to explain?
Yeah, assume that we have the same grid, in every row and column has like a symbol. We say X or O or C. X is for a wall, just like you have over there. O is for like a space you can open, you can go through it. And C will be the carrots. And I was just trying to find all the carrots. This is a problem I saw on LeetCode, I think it was.
Mhm. Wait, and you start from the middle or you start from?
Yeah, I said from the middle, but they said it was random start. Like they would put you like in a random starting position.
Okay, and then, so I think if it's going, if you can only go right and down, then it would be pretty much the same problem. You're just changing your destination, but if it's going every direction, then we might have to rethink a few things. And but that is the case, right? Like they can go up, down, left, right.
Yeah, you can go, but not diagonal. You can go up, right, left, down, but you cannot go diagonally.
So, by the way, to interject, Ariana is asking, is this a leak code medium or a hard problem?
I thought I didn't look, but it might have been a medium. I don't think this is easy.
Which problem? Your Dario's problem or the current problem on the slide?
Ariana?
Dario's problem. I was hoping
Dario's
it
problem?
wasn't an easy, if it's
Oh.
not, because I'm really behind then. I was like, oh no.
No. Dario's problem is definitely not an easy because I know that this problem is at least a medium and his problem is harder than this problem.
I think dynamic programming in general is considered like a hard, like in an interview, I don't think they'll ask that unless they're like really trying to challenge you. Right, I think.
Yeah, I also think that it's not too common, maybe in the final round, definitely the screen, I would say it's uncommon that they ask you something like this. And they're probably not gonna ask you a LeetCode hard dynamic programming question. That being said, I think it's helpful to kind of understand the general approach to be able to work through it with your interviewer.
Totally.
I completely agree with everything you have said. And Ariana and also like everyone else, don't feel discouraged that even like a medium question seems like impossibly hard or difficult. Just speaking from like a normal human perspective, like even the LeetCode medium problems are like hard, right? And yeah, and you might be daunted when you first like come across this and don't know how to solve it. But with anything else, like with practice, you will get better over time, and you will be able to like start solving some of these like even the medium level questions. Maybe not to like 100% like maybe not 100% of the time, but with much greater percentage than you probably started out with. And that's kind of like all it matters. That you just improve your kind of ability to solve problems over and over time. And yeah, and as for LeetCode hard problems, they are very, very rare in any kind of interviews. If even like us, like more like a software engineer who has been in the field for a few years, if I do encounter any kind of LeetCode hard problems, then I kind of like count that as like my unlucky day and just kind of move on. Just because like all those hard questions kind of requires like a specific tricks or patterns about that particular problem that I may not have just had a chance to study. So that will be my additional take on those like difficulties that LeetCode presents. So.
Yeah, don't like Wental said, it's just because it says medium on LeetCode doesn't necessarily mean it's medium. It can be mediums can get really, really difficult as well. Maybe they need more granular specifications than just 3 categories, but the hard ones are often, like you said, just you kind of have to know the trick. If you don't know the trick, the problem is going to be really difficult. Okay, and then anyone have any ideas on Big O?
All right, we got one guess from Dario, who said O m plus n. So n here, n as here as in like nay being rows, and m as in like Mickey Mouse being columns.
Mhm. M plus N?
Yep.
Yep, let's see.
I said n times m if you memorize.
Yeah.
Basically, if you store the
Yeah,
values.
if you use DP to memorize, then it's n times m, right? Because you're writing the entire grid.
Yeah,
Is that what you're saying,
you draw
Philip?
the grid, yeah.
Yeah.
I mean, yeah, you would put a value per value in the grid.
So then here, this is saying, depending on your implementation, the big O can vary a lot. But the one we were outlining where you're kind of drawing your way to the solution on the grid, it is capped by the raw size of the grid. Okay, oh, also, I've encountered these problems on LeetCode before. Would people find it helpful? Would you guys want me to drop a couple of links in the chat? Or is there somewhere else I should send it to?
Maybe the Slack.
The Slack?
Yeah, Dario also
Okay.
says Slack.
Cool. And also for the unique paths, I found a really good explanation video on YouTube. I can also send that to everyone. It also goes through the DP approach, since people were curious about learning more about dynamic programming. And it'll give you like a better picture of it. And it can sound intimidating at first, but really you should just think of it as like saving it's like saving computation, like in throwing back to Fibonacci, right? It becomes dynamic programming when you save the value of F3 so that when F5 calls F3 again, because F4 already called it, it just returns the value instead of having to go down that branch again. So in a similar vein here, we're just recording the number of paths at each cell so that when when we were saying in this example for D, if you know that C has 2 ways of reaching the end and you record that, D can just look at C and it ends the execution there. It says, okay, now I know I can get there in 2 steps. So, right, like if you know C can get there in 2 steps, you don't need D to trace the full step. D just needs to get to C. So the video I'll send into the channel goes through that. And I think it helped me a lot to understand it when I was learning this stuff. So hopefully you guys will find it helpful.
I do have a question about the solution of the problem we just went over. It's kind of like an easy, maybe like dumb question, but could you explain the part column greater than or equal to grid of 0 dot length? For some reason, like with rows and column problems, like grid of 0 or something of 0, I'm always kind of confused on that.
Oh, the 0 is just because it's a matrix. So you want to get not only the the m dimension, you get the n dimension, and by default that 0 can be anything. So 0 could be 1, it could be anything from 0 to the size of the first array. I think it's just convention. Does that make sense?
Does the 0 represent like the row or column?
Yeah, I think you just pick a direction. Let's say that, yeah, 0 represents the row. So if you want to find like how many rows there are, you just say grid.length. But if you want to see how many columns, you do grid 0.length. But you could do grid 1.length. It's just convention to do grid 0.length. So that's all it's saying. It's like, is the column outside of the boundary?
Okay. And then could you also explain the grid row, the last part? Yeah, that one. That's not equal to like the empty or like those quotes.
Oh, here,
Yeah.
this part. Oh, that's saying, so. Oh, it is a bit confusing, but what's really here is this. So you're saying like, if you run into a star,
Oh,
if
okay.
you run into a star, right, that's just as if you ran out of bounds.
Okay, gotcha. Thank you.
Mhm. Yeah.
Yep. So yeah, sorry that detail is kind of like went over in the presentation, but usually whenever we work with grid could be basically represented as like a matrix, which you can do by like an array of arrays. So it's an array that contains like that could contain one or more arrays. And in this case, like if we the number of like arrays in that array could represent the number of rows that you have. And then also like in each array, that length could also represent the columns you have. Right. So in like a simple example of like, let's say 4x4 matrix or grid, you could have like an array with like 4 arrays, because there will be 4 rows in there. And in the column, because the column like length is also 4, each of those array would also contain like 4 values. So that's how it could be represented. And if like, let's say this is like not a square grid, but like a rectangular grid. It's like, let's say like 4 rows and like 10 columns, then you still have like 4 arrays within that like parent array, but in each of those like child array, you could have like 10 values because there were 10 columns in there.
You guys explained it good. I just struggle with matrix problems, so I was just asking just because I struggle with them in
Yeah,
general.
no, it is definitely a harder one, for sure.
Yeah, the indices and the checking the out of bounds and all of those with matrices, it's pretty tricky. It takes it takes a lot of practice to get comfortable with it. So.
All right, seems like we reached the end. Yeah, so and then we're kind of running over time, so probably just like wrap it up here. But Alan, Curran, thank you so much for presenting this really difficult topic to everyone. And as for the fellows, hopefully this kind of first pass at Recursion made sense. If it didn't, if you still struggled with it, I'll definitely try to make another call to reviewing that lesson. No pun intended, but being recursive about the reviews might be helpful. Yeah, otherwise, I think the last slide was going to just show like the list of questions and other like websites that you could use. And it will also follow up with like additional resources to kind of help you learn this topic. Otherwise, I guess one more thing that I want to mention, we are sending out just kind of like a mid program survey. Miles have just sent it out in the channel. So please take a look and spend a few minutes to give us feedback, because we always want to know the areas in which we could be doing better, or if you have anything great to say about our program, we'd like to definitely hear about that. So yeah, please spend a few minutes to fill it out. Otherwise, once again, the lesson next week will be on a break. So we'll come back on the week after. But yeah, those are just 2 things that I wanted to announce. But otherwise, thanks. Thank you everyone for attending this lesson.
Thank you.
Thanks, everyone.
Right, see you guys.
Thanks for coming.
Yeah, appreciate the participation.
Thank you for answering my questions. See you guys next week.
All right, see ya.